All of this logic can be put together in some pretty interesting ways. But all of this logic needs variables to work with. We already know about one kind of variable, the int. Actually, we know about two kinds of variables. There's also the bool variable, but there's another kind of variable called a char, or a character, which lets you store letter values that I want to show you. Now I'm going to show you without all of this code, making things complicated. So this will print out the letter A. Right there. Notice that these are the single quote character, not the double quote character. This is different. This is what we call a string literal, and I can put many different letters in here as a string literal, but a string literal can't be put inside of a char. A char can only store one letter. I can actually store a string literal in a char star, but there are some special restrictions that you have when you're dealing with char stars. We'll get to that at some point in the future. So the letter can only have a single character in it. A happens to be interpreted by the compiler as a number. In fact, A, I believe, is the number 97. So when I compile this, it should still say A right there. I could also write this out similarly like this. This is called typecasting. I'm telling the compiler to treat this 97 as though it were a character. And when I compile it, I get A again. So if A is 97, 98 is probably B, and 97 plus 26, plus 25 is probably going to be Z. There it is. But how do we get uppercase A? Uppercase A is actually 65. Now, how do I know these things? Mostly because I've written programs like this over and over and over. But we can see all of the different values and their characters pretty easily like this. For int I equals 0, while I is less than 256, plus I. This, by the way, is the same. It's actually very, very slightly different than I plus plus, which is the same as I equals I plus 1. As it turns out, plus I happens to be very slightly faster, but that's actually kind of an arguable point based on the compiler that you're using. Anyway, let's print out all of the ASCII characters. Cout I space char I. I don't know if you heard that beep, but that beep was the result of character 7. And these are all of the ASCII codes. Character 7 is a special beep character. It's the alarm character. And there's a whole bunch of other interesting characters in here that have different looks to them. Some of them are characters that you might see when you're reading other languages, some of the vowels with accents, but there aren't any really crazy Chinese characters or katakana or anything like that in here. There's no wingdings. It's mostly just A, B, C, D, E, F. Well, there's all the letters in the alphabet. All the numbers are in here. All the punctuation marks that we have in regular English. Even the paragraph symbol right there. And some special characters here like pipes, which are useful for drawing user interface if you're ever going to make a GUI application in the console, and some other characters here as well. But some of these characters don't print out very well. 0 is actually the null terminator, and it looks the same as 32, which is a space. But 0 and 7 and 8 and 9 and 10, and what's the deal here? How come there's a space between 10 and 11? We'll get to that in a second. And 13, all of these characters, they print out weirdly. and we can see some more detail about how they print out by doing this. There's that beep again, character 7. So if we look, 0 looks like an empty space. 8, look at that. It's missing the opening bracket. It's like as soon as it printed, it took a step backwards and then put the closing bracket there. That's actually exactly what it did. 8 is the backspace. Look at all this space here. This is a tab. 9 is the tab. 10 is the new line. And 13, look, where's the end for 13? If you look, it's actually here at the beginning. The end bracket has moved from here to there. Actually, what happened is when the character 13 was printed, it pulled the cursor from wherever it was to the beginning of the line. Character 13 is the carriage return character. So some of these characters don't print very well. And what we can do to manage that a little bit more clearly is write some code in here that looks like this. Switch I case 0 C out. Actually, I can do this. Case, so it was 8 or 0 7 8 9 10 13, and actually another character that doesn't print out correctly is character 255. That's the end of file character. So when any of these happen, it's just going to break out of the switch statement, but in every other case, it will print out the character. Then it'll print the end bracket. So this code right here will account for some of those strange characters. Notice we didn't hear the beep. So 0 is a special character, so it's not being printed. 7, 8, 9, 10, 13, these are not being printed. The rest of them are. Now these special characters, they all have what we call an escape sequence. So if I made a character like this, letter equals 10, this will give me the new line character, but if I wanted to print it like this, there's no new line. I can't just print that and it won't know what I'm talking about. But if I do this, /n, this is actually the same as character 10. In fact, it's so much the same that I can do a straight replacement. Everywhere I see 10, I can literally just put apostrophe /n apostrophe. Similarly, all of these other ones, except for EOF, I don't know what the EOF code is, but these other ones have escape sequences. The null terminator, the alarm, the backspace, the tab, the carriage return, and this one is tricky. I don't know what the escape sequence for that one is. But when we're printing stuff out, for example, if I did cout hello world, I can include the escape sequences in there. I can put a /n right here, and a /t right here, and a /r right here, and a /a right there. And what it'll do is it'll print out HELLO space, go to the next line, print out WO, tab, print out RL, carriage return, which means it'll go all the way back to the beginning of the line that it's in, put a D exclamation point over WO, and then it will beep. And that was the beep that we heard. And there is the thing that happened. Another way that I could print out the ASCII table is in a table form. Right now it's in sort of a list form where it prints out all 256 of them in one long list. But I can do this. And this will take a little bit of code, so bear with me. 16. for int call equals 0, while call is less than 16. Cout. Hold on, you know what I need? I need this. I need this switch statement. Let me go back to where I was here. Cout. I'm actually going to print out a space here. Cout and L. And this should be row times 16 plus call. And this will print out all 256 characters as well. I is undefined. Oh, this should be int value equals value and value. This is all of the ASCII values, and this is a little bit more compressed. I'm going to clean this up just a little bit so that using a table format we can figure out which number each of these are. And I'm going to do that using hexadecimal. So cout 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then in here, if row is less than 10, cout row, else cout row minus 10 plus A as a character, and then print out a space. And there is the ASCII chart. And using this table, we can figure out the hexadecimal value of any of these. For example, the upside down question mark here is at row A, column 8. So if I wanted to print that exclamation point, it would be 0 cout 0x A8. And it's still running. There we go. And I need to print it out as a character. 168 is that number as a decimal value, and there it is as a character value. 0xA8 is that number as a hexadecimal value. Hexadecimal means base 16, so we usually count in base 10 from 0 to 9. Base 16 counts from 0 to F.